Hello, so today we are going to be talking about the single sample t-test. So what we'll do is we'll conceptualize the single sample t-test and we will calculate the single sample t-test. So the learning goals for today is we're going to define the t-test, we will present hypotheses, and then we'll compute and apply. So before we get jumping into t-test and single sample t-test specifically, let's contrast this to the z-score for a sample mean. Now, what happens, the reason we use t-tests instead of something like the z-score for a sample mean is t-tests, so we'll be going over several t-tests in the next few lectures. T-tests in general are used when some or all of the population parameters are not known. And so what I mean by population parameters is the population mean and or the population standard deviation. So oftentimes in research we cannot collect that information, or we just simply don't have it for whatever reason. Most of the time because we just can't sample the entire population. So a z-score for a sample mean compares a sample to the population parameters. T-tests do something similar to that, except when some of the population parameters aren't there. And so what we use is, for t-tests, we use a t-table to identify critical values, and you'll see what I'm talking about soon, instead of the z-table. And so instead of the z-table using the 1.65 cutoff, the z-scores, the t-table fluctuates based on sample size. So let's talk about the single sample t-test. So there's two basic uses for the single sample t-test. The first, it determines if a sample mean is significantly different than a population mean, with the understanding that the standard deviation for the population mean is not available. So this is logically identical for a z-score for a sample mean, with the exception that the population standard deviation is not available. A second use is to determine if the sample mean is significantly different than some expected or some hypothesized value. So this doesn't compare to the population, but compares to some preset hypothetical value. So let's give a conceptual example here. So let's say I want to know whether providing online lectures increases students' finals grades in statistics compared to other stats courses. I found that my students have a mean final score of 80, and I have 25 students in the class. However, I would use a single sample t-test in this situation when I didn't actually know the standard deviation for the population. So because we don't have access to that information, we'll use a single sample t-test instead of a z-score, or a z for a sample mean. So essentially what I'm doing is I'm taking the population of students who have taken statistics and taken a sample out of that, right, my students, and compared my sample back to the population. The other way to use single sample t-test is in an example like this. Say I want to know whether providing online lectures ensures that my class will average 85% on the final. And so that 85%, right, is a hypothetical score at this point. And so what we're doing is we're comparing that hypothetical 85% to actual student final scores on the final exam. And so what I'm doing, I'm still comparing the deviation or difference of the actual versus the hypothetical score, right? I'm comparing the difference between what the score that the students actually had, the sample, and the hypothetical score. So in this case, what I'm doing, I'm taking a sample out of the population, so my students, and then I'm comparing the mean to some hypothetical value, right? In this case, 85% for the final exam. So we've gone through and we've defined the single sample t-test, so when to use the single sample t-test and what two conditions. Now what we'll do is we'll talk a little bit about hypotheses, because hypotheses in this case are going to be a little bit different than the z-score for the sample mean. So in this case, developing hypotheses for the t-tests in general, not just the single sample, but all t-tests that you'll encounter in this class, direction of the hypothesis matters. So if the direction is indicated, so in this example, group A is greater than group B, right? We indicate that one group is greater than the other, then we'll use a one-tailed test. If direction is not indicated, A is simply different than B, we're not saying which way, then we'll use a two-tailed test. And what this does is it changes the critical value, right? So remember again, our z-score for sample mean, the critical value was always 1.65. For us, the critical value is going to change depending on the sample size and depending on the direction of the hypothesis. So again, this sort of changes the place at which we accept or reject the null hypothesis. And this matters a lot. So let's use an example here. So say I want to know whether providing online lectures increases students' finals grades in statistics compared to other stats courses. The hypothesis here is now directional, right? Dr. Collins' stats courses are greater than other stats courses. It's directional. So in this case, we would use a one-tailed test instead of a two-tailed test. However, if we state something like Professor Collins wants to know whether final grades for students who watched online lectures are simply different than students in other stats courses, this is non-directional, right? So in this case, what we're going to do is we're going to use a two-tailed test instead of a one-tailed test. So just be aware that that direction matters. Whether or not you're stating the direction, greater or less, that matters a lot in this case. So here's the basic equation for all t-tests. So all the t-tests we encounter from this point forward, the single sample t-test, paired sample t-test, and independent sample t-test, all has the same basic equation. What we're doing here is we're taking the mean of one group and subtracting the mean of another group and dividing that by the standard error of the mean. So we're comparing the deviation scores divided by the standard error of the mean. And that's going to be the basic equation for all t-tests. And so now what we'll do is we'll get into calculation and application specifically of the single sample t-test. So let's do a running example here. So let's say Professor Collins wants to know whether STEM students in his class with a sample size of 10, a mean of 3.5, and a standard deviation of 0.4 are better at statistics than other UWB STEM students who have a mean of 3.35, who have taken stats classes. So in this case, what we're doing is we're comparing the mean of the sample, which is the sample of STEM students in my class, to the mean of the population of UWB STEM students. And we don't have the population standard deviation, so we want to run a single sample t-test. So to test this, Dr. Collins will compare his STEM students' final grades to all other STEM students who have taken stats previously. So here we have our sample, right? We have 10 people in the class, 10 STEM students in my class. And we're comparing that to the population of other STEM students who have taken statistics. And for some reason, we just simply don't have the standard deviation. So this is a directional hypothesis, right? So we're saying, we're asking the question, are my students better at statistics than other UWB STEM students? So this direction matters. Are my students better? Instead of just simply saying different. We're asking a directional question here. So we need to state the null and research hypotheses both symbolically and verbally. So symbolically, we're basically saying Dr. Collins' STEM students are greater than UWB STEM students. Verbally, we'd say something like Dr. Collins' STEM students are better at statistics compared to other UWB STEM students. The null hypothesis in this case is that Dr. Collins' STEM students are either less than or equal to other UWB STEM students. And we state that verbally, right? Dr. Collins' STEM students are not better at statistics compared to other UWB STEM students. So let's think let's think about what we would do if we would not state this directionally, right? If we did this without direction. So let's use the same scenario. Professor Collins wants to know whether STEM students in his class stats grades are significantly different from other UWB STEM students who have taken stats. To test this, Dr. Collins will compare his STEM students' final grades to all other STEM students who have taken stats previously. So again, we have our sample, we have our population, but this is a non-directional hypothesis because all we're saying is significantly different. We're not saying better, we're not saying worse. We're just asking the question, are my STEM students better than other STEM students? So again, we state the research hypotheses. So are they different, Dr. Collins students and UWB students? State it verbally. And then we state the null hypothesis. So the null hypothesis would say they're equal. Dr. Collins STEM students are equal to UWB STEM students. And we simply state that verbally. So our next step here is we need to define the critical region. And the critical region is defined by your degrees of freedom. So in this case, for the single sample t-test, the degrees of freedom is the sample size minus 1. And so what we do is use Appendix B to identify either one or two-tailed critical values, right? So this, again, depends on the direction. So let's use the same example, and we'll define the critical region here. So degrees of freedom, in minus 1, we have our sample size of 10. So our degrees of freedom is 9. So if we go into Appendix B and we use our alpha level of 0.05, a one-tailed p-value would give us 1.8331. So this is the level at which we are hoping our t-value to be passed. So this is plus or minus 1.8331. If our t-value is beyond that, then we can reject the null hypothesis. So our step 3 is we need to compute the test statistic. So this is the observed deviation between the means. So, step 3A is computing the observed deviation between the means. So we have our mean, right, our sample mean, minus our population mean. So our sample mean is 3.5, our population mean is 3.35, giving us an observed deviation of 0.15. Next, we need to compute our average sampling error. So this should look fairly familiar because this is basically what we did for the z-score for a sample mean. And after calculating this, our standard deviation divided by our sample size, or the square root of our sample size, our SEM, our standard error of the mean, or excuse me, our standard error of the mean is 0.126. Now step 3C, compute the test statistic for the single sample t-test. And so what we have here is the observed deviation divided by the standard error of the mean. And here are our values here, and what we end up with is a single sample t statistic of 1.19. So if anybody at this point is wondering where I got this information from, this 3.5 and 3.35, go back and look at the scenario. The scenario discussed that the sample grade for STEM students was 3.5, sample grade for STEM population was 3.35. And then the sample size we got, we had a sample size of 10. So we compare this to the critical region, and what we find is that it is not beyond the critical region. So we reject the research hypothesis, or in other words, we accept the null hypothesis that the groups are not significantly different from one another. Our final step, or our step 4, is we compute the effect size. And so the effect size is the observed deviation between the means divided by the standard deviation. So you've seen this equation in the previous slide. The mean divided by the population mean the sample mean minus the population mean divided by the standard deviation. And this is the value that we come up with. So you also should have seen Cohen's d in a previous lecture, and the Cohen's d is going to be the same across all statistical tests. And so what we find is that a small to moderate effect. So our effect is slightly greater than 0.3, which tells us that it's a small to moderate effect. So check out the Cohen's d table for this. And now what we need to do is interpret the results. So what we would say in a section like this, if we were writing out a results section, is the average final grade of STEM students in Dr. Collins' stats course with our mean standard deviation was not significantly different than the population of STEM students who have taken stats previously with the mean. And then we have our t-value. This little 9 here is degrees of freedom, the statistics, and the effect size, the Cohen's d. So here's our degrees of freedom. Step 3 is calculating the t-value, the critical value, the critical t-value, and step 4 is the Cohen's d. So effectively what we've done in this situation is we've taken the population of students who have taken statistics, sampled my students from that population, and then compared the mean back to the population mean to ask the question, are my students significantly different than or greater than the population?